We want to make this delicious chocolate bonbons with something that would look like this, a tabletop chocolate tempering machine. The design has started, but the real challenge isn't just building the machine, it's making it temper chocolate properly and conveniently. Before we can solve that, we need to understand what tempering actually is, why it matters, and what makes it so tricky. To give you a practical look at the tempering process, I'll show you how to make fruit paste squares and then coat them in chocolate. And to explain why tempering can feel long sometimes and why it's normal, as this channel is about engineering, we'll also dive into technical details and metrics about chocolate to see why it's not that simple to temper it, but nothing too complicated. So, here are two pieces of chocolate. At first glance, they look quite alike, but only one has been tempered. One snaps cleanly and shines, the other looks dull and breaks softly. Those differences are what tempering is all about, giving chocolate its glossy finish and that satisfying snap. But you can also feel the difference when you eat them. The issue is that cocoa butter in chocolate contains different fats that melt at different temperature. They can solidify into 6 different crystal forms, but only one of these forms, the beta crystal, gives you the shiny and crisp texture that we want in good chocolate. So, tempering is the process of first melting the chocolate above the melting point of all crystal forms and then encouraging the beta crystals to dominate as it cools. There are two main ways to achieve this. The first way is the seeding method. In this method, you set aside a portion of unmelted already tempered chocolate before heating the rest. If you're starting from a fresh bar or a new pack, you know that chocolate is already well tempered and contains the correct beta crystals. After you've melted the main batch, you add back the unmelted portion. This does two things. It lowers the overall temperature and introduces plenty of beta crystals which serve as seeds for the rest of the melted chocolate to crystallize around. It's a method you commonly use with warming tanks. The problem with the seeding method is that if you put too much, it won't melt completely, leaving small chunks of chocolate that are difficult to remove. The second way is undercooling. Here, you cool the melted chocolate below the target temperature so that crystal nuclei form more quickly. But this also produces some unwanted crystal forms. So, once enough nuclei are present, you gently reheat the chocolate to eliminate the unwanted crystals while keeping the beta crystals intact. Tabling chocolate on a marble slab and scraping it up until the temperature lowers is a kind of undercooling. In the tempering process, the required temperature depends on the chocolate type because of their different compositions. They are different for dark, milk or white chocolate and can sometimes be found on the packs. Let's now see how to make these tasty fruit paste chocolate bonbons. Those are apple and dark chocolate. But you can do many different combinations by mixing the type of chocolate and fruit paste, like for example apricot and white chocolate. For this demo, I'll be using an immersion circulator, which is normally used for cooking meat, fish or fruits. So let's start by preparing the fruit paste. The ingredients are fruit compote, yellow pectin, citric acid and sugar. Sometimes you'll also see glucose syrup and inverted sugar being added. They prevent sugar crystallization, keep the texture softer and help the paste stay moist for longer. But you can still make it without those ingredients if you don't have them. Also, you may start from fresh fruits, but if it is your first time trying to make fruit paste, I would recommend to start from compote and focus on having the process correct. Using fruit compote makes it more repeatable. Let's check out the ingredients and see what each one does. Pectin is a natural compound found in fruits, but the amount varies depending on the fruit type. It's responsible for gelling, and adding extra pectin ensures that you get strong, reliable gel formation in the fruit paste, no matter which fruit you're using. Citric acid plays a crucial role in this process. Pectin only forms a stable gel in the right acidic environment, usually at a pH around 3 to 3.5. By lowering the pH, citric acid allows the pectin chains to interact properly with the sugar and water, creating a firm and stable gel structure. Without this acidity adjustment, the mixture would remain too fluid and fail to set. And then, why do we need to add sugar? And how much do we need? To answer that, we have to talk a little about preservation. Bacteria need water to grow and multiply. Fruits are rich in fibers, natural sugars, and they also contain a lot of water, which is why they spoil over time. An important indicator of a food's preservation potential is called water activity. This refers to the water that is not chemically bound to food components and is therefore available for microbial growth. The lower the water activity, the harder it is for bacteria to develop. Along with the product's pH, it's one of the main things that determines shelf life and safety. So why sugar, you may ask? Sugar is hygroscopic. Depending on the type, it can bind to up to 6 water molecules. These bound water molecules, while still present in the product, cannot be used by bacteria. Then, how much water should you use? It's a balance. Less sugar means longer cooking and more energy to evaporate water, and the paste may be less soft. More sugar protects the fruit, but too much can hide its aroma. Typically, recipes range from 50 to 70 or 80% fruit, depending on the texture and flavor you want. Now, these percentages are relative to the moist compote. You then need to remove the excessive water. To control the end of heating, you can use a thermometer, but it is more precise to use a refractometer. It's easy to use. You just put a drop of the compote onto the window, close the lid, and watch the graduation inside, which gives you the value in bricks corresponding to the amount of sugar. The more sugar concentration, the less free water. Fresh compote is around 20 bricks, and at the end of the process, you want a bricks value in the range from 75 to 80 degrees bricks. If you are using a thermometer, it corresponds to approximately 106 degrees Celsius. But the problem of using a temperature reference is that the boiling point temperature varies with altitude. Enough talk, let's quickly make some fruit paste. We'll use those quantities. So first, we mix the pectin with part of the sugar. We dissolve the acid in water and set it aside. We heat the fruit compote to around 40 degrees and add the mix of sugar and pectin. We bring it to a boil and then we add the rest of the sugar. Using a pan with a large surface area speeds up evaporation. When it gets thicker, we can start to check regularly the bricks value or temperature. Once it reaches about 75 bricks, we remove the mixture from the heat source. Next, we add the acid, which will start the jellification. So we need to quickly pour it into a silicone mold or into a frame lined with baking paper. Then we let it cool and dry for a day. Next, we can cut them in squares. I usually make them 2 cm wide. It is really large bites and 1.5 cm would probably be better. With a 24 cm square frame, that gives about 144 pieces at 2 cm, but 256 if you go for 1.5 cm. Noticeably more work to enrobe in chocolate. Let's now see the tempering process and review what is needed. We need a chocolate fork to dip the fruit paste in the chocolate. It may not be bent when you buy them, so you may have to bend them yourself. I find useful to use a toothpick for removing the dripping chocolate and then pushing the chocolate off the fork without leaving a mark. Then we also need PVC or acetate sheets on which to place the chocolates after dipping. You may cut a few decoration transfers. There are also texture sheets which exist, which can apply geometric patterns on top of your chocolates. Finally, we have a few molds ready for leftover chocolate, either shaped as bars if we want to reuse this chocolate later, or small shapes to enjoy as snacks. So, for tempering, I'll use the undercooling method. I start by melting the chocolate using a double boiler over the stove. To do that, I raise the water's temperature slightly above 50 degrees, stop the heat and place the chocolate in a stainless steel bowl on the water. I cover with a plate and leave it to melt. I sometimes reheat the water and mix the chocolate. When the chocolate is melted and its temperature near 47 degrees, I prepare 2 other containers, one with water at a temperature slightly above the working temperature of the chocolate to take into account the cooling effect of the ambient air, and one with a temperature near the low threshold, 27 degrees. It doesn't need to be exact, but if you make it too cold, you need to keep mixing without stopping, otherwise you may introduce more unwanted crystals. I transfer the bowl to the cooling container, I mix the chocolate to make it cool faster, and regularly check the temperature. Once it's near the low threshold, I transfer it to the final container and go on mixing. Finally, when it reaches the working temperature, I can start unrobing. That's it, the chocolate bonbons are ready. Of course, you can eat them for pleasure, but it can be a great source of energy when you're doing exercise and endurance work. Regarding calories, I am showing you here the approximate values. During this demo, it took 60 minutes to melt 800 grams of chocolate to 47 degrees, 26 minutes to cool it to 27 degrees, and 10 minutes to raise it again to 31 degrees. Melting time could have been made shorter, but it's easier to let this part unattended, so it's not really a problem. Now let's look at some of the technical aspects that make tempering take so long. The concepts are not difficult, but we do need to dive a bit into the physics of chocolate, things like heat capacity, phase change, heat conduction, viscosity, and also energy and power. This will help you understand the challenges, and we'll see what we can do to make the process more convenient. Chocolate has a heat capacity of about 2 joules per gram per Kelvin. That means it takes 2 joules of energy to raise the temperature of 1 gram of chocolate by 1 degree. It varies slightly with temperature, but we'll use this rounded value for simplicity. The energy required to melt chocolate, called the latent heat, is around 60 joules per gram. Note that it is the same values in reverse. It is energy that you need to remove when cooling or crystallizing. So, if we have 1 kilogram of chocolate at 20 degrees and want to bring it to 47 degrees, we need 54 kilojoules to raise its temperature and 60 kilojoules to melt it. To relate this energy with time, we need to take into account the power in watts used to heat the chocolate, 1 watt being 1 joule per second. If we were using a power of 475 watts, we would need 240 seconds to melt 1 kilogram, that is 4 minutes. For a power of 950 watts, it would be 2 minutes. And you see that it doesn't really match with what we experience. It is because those timings are correct only if we could transfer the power homogeneously to the chocolate. The reason it took so much longer time is that the thermal conductivity of chocolate is actually very low and its viscosity is high. Thermal conductivity is how quickly heat moves through a material, while viscosity describes how easily it flows and mixes with itself, like water does. The chocolate's thermal conductivity is near 0.16 to 0.35 watt per meter Kelvin. The higher this value, the faster heat diffuses. For comparison, plastics are in the similar range, while water is around 0.6 watt per meter Kelvin. Metals, however, have much higher values. Stainless steel is about 16, aluminum around 230, and copper close to 400 watt per meter Kelvin. But water behaves a little differently. Even though its thermal conductivity is only about 2 to 3 times higher than chocolate's, its viscosity is much lower. This means that in larger volumes, heat spreads much more rapidly through convection, the movement of the liquids itself. Now, for transferring the heat energy, there are 2 cases. The case we've been using is conduction, heat spreading through contact. But there is also the case of radiative transfer. This is the case of microwave ovens. The frequency of the electromagnetic field generated inside is 2.45 GHz, which corresponds to a wavelength of 12 centimeters. Also, there is not much water in chocolate, only 0.5 to 1.5%. It's mostly the water inside the chocolate that is heated and conveys heat to the cocoa butter. And the penetration depth of the electromagnetic wave in chocolate is about 0.5 to 1.5 centimeters. Because of this, melting is faster inside the microwave oven, but it doesn't do anything about the low thermal conductivity of chocolate. As long as you keep applying power, that first layer of chocolate will melt and get really hot, while the inside will slowly heat up. So the way is to use a low power setting and take the chocolate out regularly to mix it. Now, how can we state this problem of the microwave in simple terms? The problem is that there is no temperature regulation inside the microwave. On the contrary, with a warming tank, if you want the metallic tank temperature to be at 50 degrees, it will apply the full available power until the temperature reaches the target, then the power will stop and adjust its level to maintain the temperature limit. Now, to know how much power we can push through chocolate, we need to take a look at the equation of heat transfer. The rate of heat flow, that is the power transferred in watts, is the thermal conductivity multiplied by the surface area multiplied by the temperature difference and divided by the thickness. If we consider a tank at 50 degrees and chocolate at 20 degrees, when we put them in contact, heat starts to flow to the chocolate. We'll consider the first layer of 1 mm and rearrange the equation to calculate the surface area needed if we want to be able to transfer 400 watts of power. For that power, we need a surface area of 530 square centimeters. This is about a square of 23 centimeter side. Using this surface area as a reference, we can check how much power can be transferred for the different temperature differences. We see that the power that can be transferred reduces a lot. At 30 degrees, we can transfer 266 watts, and at 40 degrees, 133 watts. As we have seen before, viscosity is high, so the chocolate doesn't move near the tank interface, and heat conduction is low, so the side will get hot while the inside stays cold. So the correct way to mix chocolate to get the maximum power transfer is to scrap this first layer and push the cold chocolate at the interface. That's why tabling is used. Marble or granite slabs have high heat capacities, meaning they can absorb a lot of energy without their temperature rising too much. By spreading the chocolate over a large surface and scraping it regularly to expose a fresh layer, you can reduce the temperature with a high cooling power. That's why this traditional method is so fast. Now let's take a quick look at the current design state. It's going to be a first iteration, so it's not perfect. But if we check the model, we see a few things which make it convenient. First, it has precise temperature regulation, which can heat, cool, or provide a stable temperature. An infrared temperature sensor is integrated for hands-free temperature measurement of the chocolate. No need for a separate thermometer. The integrated lid can be used during heating or when it has reached the working temperature to keep it tempered when it's unattended. There are also blowers to have a layer of hot air on top of the chocolate to limit cooling of the top layer by ambient air when the lid is open. So we'll see how it goes. The next step is building the prototype and testing how convenient it is. Thanks for watching. See you in the next one.